Hi, I'm Ju, a senior in material science and engineering, and I'm presenting my honors capstone project of atomistic simulation of dislocations in magnesium and magnesium alloys with a subtitle of Interaction between neutron clusters and dislocations. Before I go into any detail of this project, let me walk you through some of the terminology that will be useful. The first one is dislocations. You can simply understand dislocation as one-dimensional defect in materials, and a dislocation is just irregularities within a crystal structure. The presence of dislocations will decide the mechanical, thermal, and irradiation performances of materials. And by studying them, we can manipulate material properties to suit our needs. There are two common types of dislocations, edge dislocation and screw dislocation. And in this project, we only make use of the screw dislocation here. So why do these dislocations exist? Well, from a thermodynamic perspective, they can reduce the total energy of the material by transforming the small amplitude and spatially diffusive distortion into large amplitude and spatially localized distortion. So to put it in simple words, nature always prefers lower energy states, and the existence of dislocations serves that purpose. From a kinetic perspective, these dislocations can facilitate plastic deformation by reducing the energy barrier and required stress to propagate the plastic deformation. So what is screw dislocation? Well, they can be understood by literal meanings, where the structure simply rotates with respect to a slip plane, leaving some of the atoms have higher elevations than others. And the last concept we need to understand is what is ductility. Ductility is the material property that measures its ability to plastically deform without fracture. So to put it in simple words, it indicates how soft or malleable the material is when subjected to a external force or impacts. And so the motivation behind this project really comes from the excellent properties of magnesium alloys. Magnesium is a lightweight structural metal that often used in automobile or aerospace industry. We can see from the top left figure that it has high strength, but pure magnesium exhibits low ductility at room temperature, preventing us from further usage in large-scale productions. And recent research have found out that alloying rare earth elements like yttrium can activate more slip systems and lower the general stacking fault energy, which means that it will improve the room temperature ductility. And the reason we are interested in clusters specifically is because we believe that there might be a possible new strengthening mechanisms behind it, apart from solid solution strengthening and precipitate strengthening. And the current issue with magnesium alloys is that they have low ductility or creep resistance, and it's very easy for them to catch on fire. We do not care about the other two issues in this project, only the ductility part. And the middle column shows a general workflow of the whole project. So the first step would be, for me, would be to naturally observe the clusters in bulk magnesium and then introduce a dislocation to make it a defected system. Once I integrate these two steps, I can apply different external conditions, such as different shear stresses and different temperatures to the system to see how their interaction affects the gliding of dislocations. On the right, I've listed some specific goals that are the most important within each step. So to observe the clusters in bulk magnesium, I need to perform a hybrid Monte Carlo and molecular dynamics simulation in semi-grand canonical ensemble. In this context, molecular dynamics serves the purpose of relaxing the whole structure, while Monte Carlo simply means I'm swapping the magnesium atom and yttrium atoms. And the purpose of this hybrid MC-MD simulation is just for the system to reach a equilibrium concentration of yttrium that I want. The next step, when I introduce the dislocations, I confirm that the stacking fault width is consistent among different research methods such as MD-DFT and experiments. And in this manner, I can confirm the solute-solute interaction between magnesium and yttrium. And the last step would be to validate the stress strain curve to make sure that I have a reasonable simulation result. So this is my simulation setup. I input 2 screw dislocations into the system, and you can see the dimensions there. And I'm using a 300K room temperature condition with a EM potential. So here are some of the preliminary results that I was able to get from this project. You can see so the first figure is the evidence of existence of clusters. The red atoms are magnesium, while the blue ones are yttrium. And you can see they like to form in small groups rather than large groups, which are called precipitates, or randomly dispersed, which are called solid solution state. So this is the direct evidence of clusters in magnesium. On the right, different color just means different clusters identified by the cluster identification algorithms. And from this simulation snapshot, I was able to propose a possible phase match according to the phase diagrams. I divided all the clusters into 2 categories, large ones and small ones. Large ones has over 15 atoms, while small ones have less than 15 atoms. So if we look closely into this histogram, we can see that the large clusters have a estimated yttrium concentration of around 33%. And also by comparing their Euclidean distances and specific structure, the large cluster can be magnesium 2 yttrium, and small cluster can be magnesium yttrium. On the top right, this is the evidence for solute-solute interaction between magnesium and yttrium. So the simulation snapshot shows that the yttrium atoms, which are colored in yellow, like to form around the dislocation lines, which are colored in green and white. And we can see from the line plot that the yttrium concentration is much higher than anywhere else in the system. And along the way, I was also able to get the critical yttrium concentration to form clusters. So namely, in bulk EAM, they are 0.3 atomic percent, and bulk MEAM 0.2 atomic percent, defected EAM and defected MEM both have 0.1 atomic percent. So that's how far I was able to get within this project. Some future work would be to apply external conditions as well as looking for solid segregation and interaction models. And the long-term goal for this project was will be first to conduct further simulations with applied shear stress and different temperatures, and then propose a non-rare earth element as replacement for yttrium because rare earth elements are expensive and we cannot use them for large-scale productions. And then hopefully we'll be able to design cheap and ductile magnesium alloys. I wanted to say thank you for Dr. Liang Qi to provide guidance and resources that made this project possible, and also Mr. Tony Wang, who provided financial support during the summer, and Vaidehi, who provided suggestions on LAMP script writing. So I initially get involved in this project through the summer research program in College of Engineering. And what hurdles most or the most difficult part is probably the setup of the simulation. It took me around 2 days to install the LAMP's simulation software and then numerous trial and errors to get a reasonable simulation result. And also these simulations are all run by supercomputers like Exceed and Gray Lakes, and we have to wait for a considerable time for each simulation to finish.